Okay, here we are back again. This is chapter 3, Physics 125. This is the last skills chapter. Then we'll get into the real physics in chapter 4. I can't wait. I'm sure you can't either. This chapter is about vectors, and vectors are very important in physics. We use them all the time, and so it's important for you to understand how to work with vectors so that when we get to the physics, this will not be a challenge. So we got the picture of a vector here, right here on the front slide here, this black vector with a V, it's a velocity vector, and it's at some angle, right? So say we're throwing a baseball up into the air. And so there's some angle, and then there's an arrow, which we're going to talk about, and then you see how it forms into a triangle. So this is where we're going to do some right triangle trigonometry. It's not really real trigonometry. It's simply solving right triangles, which you did in geometry, you did in lots of other courses, math courses. We're really not going to go beyond SOHCAHTOA. So first we need to define what a vector is, and to do that we're going to start by defining what a scalar is, because really scalar versus vector is the distinction that helps us understand what's going on. So distance is a length. It's a length along some path that we would talk about. So say from A to B, you wander from A to B and you follow that white line, and that white line might be 20 meters long. And so it's a scalar quantity. It has a size, right? 20 meters versus 30 or versus 40. It has a unit. It's 20 meters, not 20 feet. So those are some examples of scalars. And distance is a scalar. Speed is a scalar. Volume, height, age, all these things are scalars. They're a number and a unit, and that's it. On the other hand, a vector is more than that. A vector is still a number and a unit, but it also has a direction to it. So to go from A straight to B would be not 20 meters, but only 12 meters, and it's at an angle of 20 degrees above that horizontal line. So there's a direction to it, as well as a size and a unit. Magnitude, direction, and that's going to be described by a number, a unit, and an angle very often. Sometimes we describe the direction in words. We can say west, we can say east, we could say up, we could say down, but oftentimes in the physics problems, it's going to be distinguished with an actual angle. So we'd have 12 meters at 30 degrees or 8 kilometers per hour north. Okay, so this is where it's a little subtle. Speed and velocity are closely related, but velocity is a vector and includes direction. Speed does not include direction. Likewise, distance and displacement are closely related things. Distance was a scalar, whereas displacement is a vector. So if you go 4 meters east and then 6 meters west, I draw that out here, 4 meters east, 6 meters west, you go plus 4 in the x direction, then you go minus 6 in the x direction, you end up at minus 2. So you end up with a displacement that's 2 meters west, but you end up with a distance traveled of 10 meters, right? 4 meters forward and then 6 meters backwards, you travel a total distance of 10 meters. So this helpfully demonstrates the difference between distance and displacement. I'm gonna get another example here on the next slide. The idea of a track, right? You run around on a track in high school. Usually 4 laps is a mile or 1,600 meters. And you go round and round and round, right? But there's no point at which you're ever a full mile away from where you started, or even a half a mile away from where you started, right? If you took the straight line distance from where you start to where you end, or to where you're standing, it's always going to be some smaller distance. But if you complete enough laps, you'll go a mile or 5 miles or whatever. I always find it interesting, you know, on Memorial Day weekend, they usually run the Indianapolis 500, and Memorial Day weekend's a 3-day weekend. Sometimes I go and visit my my in-laws that live in Ohio, and they live 500 miles away from me. And so I travel 500 miles, but I travel a distance of 500 miles to get to their house. My odometer is going to read 500 miles, but I'm also displaced 500 miles from my house. The roads go fairly straight. I'm 500 miles from home when I get to their house. the drivers in the Indy 500, they go round and round a 1.25 mile track, and they go around it 400 times, and 400 1.25 mile laps is 500 miles. So they go 500 miles, but they never get anywhere. Their displacement at the end is still zero. Now, I can say that, but at the end of the weekend, what do? I get back in my car and I drive all the way home. And so I come back that same displacement of 500 miles. So when I get back to my house, my odometer reads 1,000 miles, but I'm back where I started on Friday afternoon. So it's a similar concept, but distance is what your odometer is going to read, and displacement is your measurement from some fixed point, whatever you decide to be the measurement location. Obviously, in our problems, that's going to be the origin of graph paper, right? 0, 0. But in real life, you've got to decide where you're measuring your distances from. Some of us might use our home. Some of us might use a nearby large city or something like that. So here's just another list of scalars and vectors. It's actually a list from NASA. These are a lot of things that we're going to work with at different times in this class, right? So length and area and volume, we've talked about those already in the previous chapters. Speed, we'll talk about some. Mass, certainly density, pressure, temperature. All of these are very useful and important numbers that have units on them, but they are scalars. They don't have a direction. You don't say the box has, a 2-liter volume up or a 2-liter volume at 25 degrees north of west. You just say it's got a 2-liter volume. That's all there is to it. Whereas the vectors all have to have direction, right? If you are moving with a velocity, you have to be going in a direction, and that direction needs to be stated. Or if you're accelerating, your velocity is changing in a particular direction. Is it changing forward, making you go faster? Is it changing backwards, making you go slower? Is it changing sideways, making you turn? These have direction, right? Force, a push or a pull on something, that's going to be in a particular direction. So vectors have direction included in them. And one of the ways we specify that direction can be with a compass, right? If we're just talking about displacements, on a coordinate plane, we can use the cardinal directions of the compass. So this green dot is 50 degrees above the direction of east. So we say that it's 50 degrees north of east, and it might be 40 meters in length. So 40 meters in length is this arrow, and it's at 50 degrees north of east. It's a little non-intuitive to some people to say the direction that way. It makes sense when we say it out loud, north of east. But when we go to write it or think about it, we have a tendency to think about the east part first, right? Well, we're measuring this angle from east, so people want to start with east. But that's not really what you're supposed to do. You're supposed to start with, which direction am I going away from east? Am I going up toward the north, or am I going down toward the south? So it's 50 degrees north of east. 50 degrees south of east would be a very different location. And 50 degrees east of north, 50 degrees east of north would be pointing in a different direction as well. So this is fully defined, but we need to understand what it means. We start at the second direction and we measure toward the first direction. We start at east and we measure toward the north. We start at west and we measure toward the north to get 60 degrees north of west. We start at south and measure toward the west to get 60 degrees west of south. And that's 6 degrees south of east. Now you will notice that 3 of these 4 got measured off of the east-west line, and that is what we are used to doing. But it doesn't have to be done that way. You can measure off of the vertical line. It's one of those things that catches people because 90% of the time we do it one way, and then that other 10% tends to catch people, and they tend to get confused when that occurs. There's nothing wrong with this. We just have a tendency to do it, a convention of doing it mostly off of east-west, and very much more so when we're talking about above a surface, right? When we're talking coming off of the ground, we almost always measure the angle from the horizontal surface, but that's just the way it is. So Here's a couple of them drawn out for you. Take a moment, write what you think these angles would be described as, and then we'll look at the answers. So we start with the second direction. So this would be starting in the east and measuring toward the south. So we're going to say south of east, and it's 50 degrees. So 50 degrees south of east. And likewise here, we're measuring toward the west. So it's west of north, 45 degrees west of north. Vectors can be represented in many different ways in physics. We oftentimes like to just put a little arrow above the variable when we're writing on the chalkboard or on paper to remind ourselves that a vector has direction. Arrows are the classic representation of a vector because an arrow implicitly has direction, right? If you put an arrowhead at the end, then it is pointing in a direction, and that shares that information. So when we're drawing them, we draw arrows sometimes, or we draw an arrow over the variable to indicate that it is in fact a vector. That's not easy to do on a computer or in a book, and so in a computer or a book sometimes they will boldface the vectors. So see, these are bold-faced as opposed to the regular text, which is not. That's not helpful on the chalkboard or on paper because seeing what's boldface and what's not is not obvious. So there's these two different conventions. Again, I wish there was one instead of two, but there are two, and so I'm making you aware of it so that you can read your textbook and understand what they're doing, and also see written out work and understand why it's slightly different. The Cartesian plane we're going to use significantly in our two-dimension vectors. You learned about this in math class. It was named after René Descartes, who was a famous French mathematician and physicist, and we use it to express vectors. So it's an XY plane, but we talk about the coordinates in a particular manner, right? So this first quadrant, the quad, 4, quad meaning 4, and there's 4 sections. The first one where we have positive x's and positive y's is called quadrant 1. And in the early days of your math classes, you primarily worked in quadrant 1. Everything was positive, life was good. You drew little triangles here and everything was wonderful. But eventually you have to deal with the fact that there are negative numbers, and that's part of life. So you will notice here the way they've numbered the quadrants. The upper right one is 1, the upper left one is 2, the lower left is 3, and the lower right is 4. And that is because we are supposed to move around the Cartesian coordinate system in that direction, in the counterclockwise direction, starting with the positive x-axis, or if you think about it in terms of a clock, starting at 3 o'clock and running counterclockwise around the system. That's the order that you go through the quadrants. And that is how sometimes they measure the angles, right? They start the angle at the positive x-axis and they go around. So if they tell you 30 degrees north of east, then you know where that angle is. If they tell you that it's 50 degrees north of west, you know where that angle is. But if they just tell you the angle's 135 and they don't say anything else, they are assuming you know about Cartesian coordinates and that 135 degrees starts at the positive x and it swings around to where 135 would end up in quadrant 2. So we're going to learn about vectors and how to add them and how to combine them in various ways. So there's the tip-to-tail or tail-to-tip method of adding vectors, which is very visual and very helpful to think about when you're adding vectors. So this is a diagram of adding vector 1 to vector 2, the green vector to the red vector. So the first thing you do is you draw your first vector starting at the origin. So our first vector is green, it's 7 units long, it's 50 degrees north of east. So north of east is going to swing us up here, and then we're going to measure out 7 units using some kind of scale or something like that. And we're going to put an arrowhead to show which direction the vector is going. And then this is where the tip to tail part comes in. We take our second vector, which is 3 units south of east, and we start it where the first one ended. We start our second vector where the first one ended. It's kind of like follow the leader, right? I think of it a lot in terms of, following a treasure map, right? So it says, start at the big oak tree and take 50 paces east and then take 10 paces north. So you do the first instruction, and then where the first instruction ends, you start your second instruction. And when you get all done, you will be at the answer, right? And our goal here is to get the answer in one step instead of in 2 or 3 or 50,000 steps following the treasure map. So we draw our first vector, and then we draw our second vector starting where the first one ended. So it's 3 units long, and you will see that's the direction east. So 35 degrees south of east is going to be down here. And then when you're done, you know, here we were only adding 2. You could add 3 or 4 or 50. When you get all done, then you draw the resultant. The result is what you get from the addition, right? The blue vector is equal to the sum of the green and the red vectors. You draw it from your original tail to your final tip. So you're going to end up with 2 tails at the beginning and 2 tips at the end, and all the other points are going to have exactly 1 tail and 1 tip. You don't want to draw it the other direction. That would be the vector that would take you home, right? We're not talking about going home. We're talking about an equivalent vector to these 2 pieces. So here's some more graphical representations. Just driving home the point, if A plus B equals C, we can do A first and then B, and we get C, or we can do B first and then A, and we still get the very same C. So the order in which you add the vectors does not matter, as long as you add them correctly. And here we have a slightly more complex adding 3 vectors, right? So we can do D and then E and then F, and we get an answer G. So you see here G actually, you know, overlaps the combination of vectors. Or we can do F and then E and then D, and G still ends up pointing in the same direction and being exactly the same length as the previous one, which is what we would expect if these are truly equivalent expressions, and they are. So that's great from a pictorial standpoint, and pictorial standpoints is good, and I might post a practice worksheet with some pictures, some vectors to add with pictures in that way, and I'll post the key as well. But we are ultimately going to move on to numbers, right, to actually using the values of the vectors, and this will allow us to do these problems without getting out graph paper and measuring everything out very carefully to scale. And to do that, we're going to need to use right triangle trig. And I promise we're not going to go any further than the right triangle, right? So this is a right triangle. It's got a right angle, and it's got a hypotenuse that's across from the right angle, and then it's got 2 other smaller angles that have to add up to 90, right? Because all the angles of the triangle have to add up to 180. So this is right triangle trig. Sometimes it's referred to as SOHCAHTOA. That's the mnemonic that they use to teach you this relationship. And people get all distressed at times about trigonometry and how to do it. But really, it's no different than the simple equations that we used in the problem-solving chapter, right? We had VT equals D. Most people are pretty comfortable with VT equals D, velocity times time equals distance. But there's 3 variables there. There's velocity, there's time, and there's distance. And if you know 2 of the 3, you can solve for the third. If I say 70 miles an hour for 3 hours, you can do 70 times 3 and get 210. If I say I went 250 miles in 5 hours, you can divide and tell me what the velocity is. You can solve for the one unknown if you have the other 2 values. And the same thing is true in these sine and cosine SOHCAHTOA relationships. Just one of the variables is an angle, and you have to use your calculator to do the trig function. You can't just do it mentally, or it's not simple multiplication. There's just another processing step, but your calculator does that for you, just like you might have typed in your calculator 250 divided by 5. The calculator will do the sine and the cosine step as well. So we call it SOHCAHTOA because the sine of the angle, so here's where they measure this angle theta, okay? The sine of that angle is equal to the ratio of 2 of the sides of the triangle, okay? That's what they have been able to figure out. So sine of the angle is the ratio of the side across from the angle, opposite of the angle, divided by the hypotenuse. So again, the longest side of the triangle is always called the hypotenuse. It's across from the right angle, the longest side. But for each of the individual angles, the smaller angles, there's then two other sides that we have to talk about the relationship with. So the side that's across the triangle, I think of it as sitting at the table, right? Sitting at the table with the family. There's somebody sitting across the table from me. They're opposite from me. And then there's somebody who's sitting right next to me. They're adjacent to me. Yes, the hypotenuse is also adjacent, but it's the longest side. It has a different name. We call it the hypotenuse. So there's one side that's right next to me. It's adjacent. There's one side across from me. It's opposite. So the sine of the angle is the opposite side divided by the hypotenuse. The opposite side divided by the hypotenuse is sine. So that's why we call it SOH, S-O-H. S for sine, O for opposite, and H for hypotenuse. So that description is always the trig function, and then the numerator, and finally the denominator. So SOH is for sine, opposite over hypotenuse. Ka, C-A-H, so ka, toa. C is for cosine, A is for adjacent. This is the side adjacent to the theta, so it goes in the numerator. And then H for hypotenuse. So the hypotenuse here is represented by R. So cosine of theta is equal to the adjacent side divided by the hypotenuse. And then finally TOA, T-O-A, tangent of the angle is equal to the opposite side divided by the adjacent side. So that's the relationship. There's really four variables, right? There's three sides, and then there's an angle. So there's four variables, and that gives us three relationships. Each relationship relates three of the variables. Each one is missing one of the variables, right? This one is missing the x, this one is missing the y, this one is missing the r. And there's a relationship that's missing the theta. That's the Pythagorean theorem relationship, right? X squared plus y squared equals r squared. The sum of the square of the sides of a triangle is equal to the square of the hypotenuse. So we actually have four relationships. Each one is missing one of our four variables. Now you will see I have additional relationships written here. And that's because we don't usually end up using this version of sine, right? We do a little algebra. We move the r to the other side. So if we multiply both sides by r, the r cancels on the right side, and it shows up over here on the left side. And that's how we more often use it, right? We're more often being given a vector, and we're told the length of the vector, and we're told the angle of the vector, and we want to find the pieces of the vector. So this is just the way we more often use it, right? Remember, in our problem solving, we have to find the equation, and then we have to solve the equation for the unknown that we're looking for. Well, the reality is we're usually looking for opposite and adjacent. And so this is just the way we'd prefer to use the equation, because then it's already solved for what we're interested in. Please take note in your calculator, there's two different ways to do trigonometric functions. There's degrees and there's radians, and we are doing it in degrees primarily in this course, and so you'll need to have your calculator in degrees, and we'll talk about that a little bit later. But if you want to test it now, if you type sine of 30 into your calculator and hit enter, you should get 1/2. And if you don't get 1/2, then that means your calculator is in radians, and there's a mode button usually on your calculator that you can click on, where you'll be given the option to change from degrees into radians. So here's an example problem that is just going to use one of these trig functions to allow us to solve the problem, so we can see how it works. So we've got a building that's some unknown height, h. We don't know how tall the building is, but we do know that the sun is creating a shadow. And if we go to the end of that shadow, which we can measure because it's on the ground, and things on the ground are easy for us to measure, the shadow is 90 meters. And at the end of the shadow, we use that's not a protractor, whatever the device is called, we use it and we measure the angle that the sunlight is making. So we have this angle of 30 degrees, and we have the length of the shadow, and we want to know the height of the building. So again, we have two variables, and then there's a third we want to know. And so we look at our equation, or variables that have been given. We've been given the angle, so that's good. We've been given the length of the shadow, which is next to the angle. So we've been given adjacent, and we've been given the angle, and the h is across from the angle, so that's opposite. So we have the angle, and we have the adjacent, and we want to know the opposite. So we need the trig function that has opposite and adjacent in it. That's not so. So has the h in it for hypotenuse, and we don't have the hypotenuse, and we don't care about the hypotenuse. It's not ka, the h is in that one too. It's toa, because toa has the o and the a for adjacent and opposite. So that's how we conclude that we want to find the opposite side, and we know the adjacent side, so we go with tangent. Tangent of the angle is opposite over adjacent. Tangent of 30 is h, which is the opposite side, divided by 90, which is the adjacent side. We then bring the 90 to the other side, multiply by 90, that cancels out, multiply by 90, and we have 90 times the tangent of 30 equals h. Now we can plug that into our calculator. The calculator will do all the math for us and tell us that the building is actually 52 meters tall. But again, we are going to primarily be solving for the components of a vector. And so the vector is going to be given to us as the hypotenuse and an angle, right? We just did some practice ones like that, right? 40 meters at 50 degrees north of east. Well, 40 meters would be the length of the hypotenuse of this triangle, and 30 degrees would be that angle. So we want to find x and y, and we'll talk about why we want those in a moment. But again, this is how we're going to go about finding them, using the trig functions, sine and cosine, using so and ka. And this is going to convert from something they call polar coordinates. To say that we have the hypotenuse and the angle is described sometimes as polar coordinates. Rectangular coordinates is going to give us things in terms of x and y, right? The sides of a rectangle are x and y, so we call them rectangular coordinates. So if a person walks 400 meters in the direction of 30 degrees north of east, how far are they displaced east, and how far are they displaced north? So that is essentially giving us the triangle with a hypotenuse of 40 meters and an angle of 30 degrees. And we want to find the x side, which is the displacement east, and the y side, which is the displacement north. So the x side is adjacent, so we're going to use cosine. X equals r cosine theta. It was x over r equaled cosine theta. We moved the r over. And for the y component, we're going to use sine instead. Sine goes with opposite, cosine goes with adjacent, okay? Now you might be tempted in time to start thinking, oh, cosine goes with x and sine goes with y. That is true if and only if the angle is measured from the horizontal, okay? If we would measure the angle from the vertical, then the side opposite the angle would be the x, and we would be using sine to get x, and the side next to the angle would be cosine. Would be y, and we'd be using cosine to get y. So just be very careful. This relationship is always true. Cosine is always adjacent, sine is always opposite. The x and the y's are not always one or the other. So again, we continue our calculations here, and they're working through this step by step so that we can understand what's going on. So x equals r cosine of theta. The r is the hypotenuse, 400 times the cosine of the angle, 30 degrees, gives us this value, 346 meters positive, and that's in the east direction. So 346 meters east. And sometimes we'll write that as the variable for the hypotenuse, which was r, and then with a subscript x. So the x part of this hypotenuse is 346 meters. And then we do the same thing for the y. 400 times the sine of 30. As I mentioned, the sine of 30 should come out to be 1/2. So 1/2 of 400 is 200. 200 meters, and this is positive 200 meters, and positive y is going up. That's in the north direction. So that can be written as the y component of r is 200 meters. All right, both of them are positive, so we are in the first quadrant, right? That first area in the upper right where we would be if we were measuring from the east around toward the north. We'd be in the first 90 degrees. And so we're 30 degrees is our angle. So the person has been displaced 346 meters east and 200 north of the original position. So again, they're just going to rehash here what signs you're going to get in the various areas. We already discussed that in the first quadrant, both the X and the Y are positive. But if you go to the second quadrant, the Y is still pointing up, but now the X is pointing backwards. And this is going to be angles, if we're measuring the big angle, remember starting with the positive X direction going all the way around, this is going to be angles between 90 and 180. And you will end up with a negative X value and a positive Y value. So again, if you want to test this with your calculator, take some number. You can take that same 400 that we had. 400, the cosine of 110, and you will see your calculator will give you a negative value to tell you that you're pointing in the negative X or left direction. But if you do 400 sine of 110, you'll still end up with a positive value because you're pointing upwards. Some people don't like to use large angles like that. They will sit there and go, oh, 110. Well, I know my geometry. I know my supplemental angles. If this is 110, then this angle right here must be 70. And so then they do the little triangle with the 70 degrees. And that's perfectly fine, except for when you're in that little triangle and you're using the little angle, both of these values are going to come out positive, which is appropriate because within the triangle, from that 70-degree angle standpoint, this is moving away from it, okay? But you are going, if you do that, if you make the little triangle, then you're going to have to remember to put the appropriate signs in as needed. If you just use the big angle, the signs will appear automatically for you. So then we get to the third quadrant and we're both going to the left and going down, so they will both be negative. And finally, in the fourth quadrant, now we're back to positive X's, but now negative Y's. And again, so if you plug into your calculator the angle of 300 degrees, 400 times the cosine of 300 degrees, you'll get a positive X, but 400 times the sine of 300 degrees will give you a negative Y. Now, why do we do this? Why do we like to get things in X's and Y's? Well, the answer is that when we go to add two vectors, it's really easy for us to add X's and Y's if we have both of them in those terms. Remember, we talked about at the beginning of this process about going 4 meters east and then 6 meters west, and that was very easy for us to add together, right? Because those vectors were running parallel. They were in opposite directions, but they were parallel to each other, so it was very easy for us to subtract them and get the answer. And that's why we like to convert all of our vectors into rectangular coordinates, because then we can add them very easily. But then when we're done adding them, we're going to want to go back into the original vector configuration. So now we're going to talk about how to go from X and Y back to R and theta. And it's using essentially the same process, but in reverse, right? So again, this is the ignoring the angle approach, right? The square, the sum of the square of the sides equals the square of the hypotenuse. So if we want to find the hypotenuse when we know X and Y, we do X squared plus Y squared, and we take the square root of all of that. That's Pythagorean theorem. That's solving the Pythagorean theorem. Now, if we have X and Y and we want theta, we're going to want to use the tangent function, right? Because tangent TOA uses X and Y, or opposite and adjacent, but doesn't use the hypotenuse. So the tangent of the angle equals Y over X, because Y is opposite, X is adjacent. So how do we actually get the theta all by itself? Well, we use something called the inverse function. So an inverse function will always undo any function. It's the opposite, right? We learned addition and then we learned subtraction. We learned multiplication, then we learned division. We learned to square, then we learned to square root. Every function has a opposite function or an inverse function. And the same is true of tangent. So we'll take the inverse tangent of tangent and those two will cancel. So we'll take the inverse tangent of this side and that will give us our answer. And we'll see that again here in a moment. So here we've got an example problem with forces instead of with distances or velocities. Again, we're not just learning vectors for chapter 4. We're learning vectors because we're going to use vectors in chapter 4, and then in chapter 5 and 7 when we do forces, and also in chapter 6 when we do momentum, and lots of other places throughout the course. So this is an important skill. Here we've got an example problem that's about forces, okay? Forces or pushes or pulls. So we've got an animal that's being pulled on by two different people trying to get the animal to move, and we want to know what the net or total force is from these two different pulls. So this note is just reminding us that forces are vectors also, so we can treat them in the same way. So here we have our obstinate donkey who doesn't want to move, and we have two people pulling on the donkey with 40 pounds and 30 pounds of force respectively. Why they aren't pulling in the same direction, I'm not sure. That's up to them. And again, if we do these things by appropriate scales, then we can do it graphically, but our focus here is on being able to do it mathematically without having to have everything scaled perfectly. So we've got a positive x of 40 pounds and we've got a negative y of 30 pounds, right? Down is negative y, left is negative x. And then we arrange them tip to tail, right? More useful. If you draw it like this, you will be tempted to complete this triangle, right? All of this is about triangles. So you will be tempted to complete this triangle. And when you complete this triangle, you will in fact get the right size force, okay? Because this diagonal of the rectangle is the same length as this diagonal of the rectangle. The problem with drawing it like this and solving it like this is the direction. You get real confused on the direction because these arrows tell us that our answer should be down and right. And if you draw a line right here, you can't make that line down and to the right. You can make it down, but then it's going down and to the left. Or you can make it to the right, but now it's going to the right and up. So it's not working. And it's not working because we have our two tails together instead of drawing them tip to tail. If we draw them this way, you know, this is not physically what's going to happen, right? It's not like the first person pulls and then the second person pulls, but it's what we need to do to find the mathematical equivalency. So we draw our first vector, and then we start drawing our second vector where our first vector ended. And now we make a triangle, and the side of that triangle is the right length, and it's also clearly in the right direction. We're going right and we're going down. And this line can clearly be drawn as going down and to the right by putting the arrow on that end of it. Now, how you measure that angle, there's two ways to do it, right? We can measure the little angle inside the little triangle, which they're using phi for, or we can measure using the Cartesian coordinates, the theta that's going to go all the way around and be in the 300ths. So again, to go from sides to a hypotenuse, we do x squared plus y squared, or r component of r squared, the x component of r squared plus the y component of r squared. We'll then take the square root, will give us r, so 40 squared plus 30 squared, square rooted is 50. And then we take the tangent of phi will equal opposite, which is 30 over 40. And if we have the negative sign in there, that will give us negative 36.9. Again, we solve this. They don't show that step explicitly here. The inverse tangent of both sides. So if you take your calculator, you have a button on your calculator that says tangent, and usually that very same button is used for inverse tangent. There's a little button in the upper left of your calculator that's a second button, which will let you access the secondary function of each button. So if you press second and then you press the tangent button, you'll get tangent with a little -1 above the n, at the end of the n. And that means inverse tangent. So you take the inverse tangent and then you put in parentheses 30 divided by 40, and it will give you this value. So if the phi is 36.9, then that tells us that theta will be 360 minus that, or 323.1 degrees. I don't care which one of these angles you give me as long as you explain correctly the angle. So you could say 36.9 degrees south of east, or you could say 323.1 degrees, and that's all you would have to say. You wouldn't have to give any direction. So that's why some people like the Cartesian coordinates, because all you have to do is give the angle. Unit vector notation, this is just a way of thinking about these rectangular component parts of the problem. So we have 3 dimensions. I'm not going to do 3-dimensional problems very often in here, mostly 2 dimensions, but here we're just going to go over the 3 dimensions. So we have x, we have y, and then we also have z. And this idea of unit vectors is coming off of the principle of multiplying by 1, right? So if you multiply something by 1, you don't actually change its value. So I is a vector pointing in the direction of the positive x-axis that's only 1 unit long. So that's just basically giving us our direction. So then we can multiply any scalar times that vector, and we'll get a vector pointing in that direction of the length that is equal to our scalar. So if we write 12 times I, and we have a vector that's 12 units long pointing in the positive x direction. And the same thing for j. J points in the positive y, and k points in the positive z. So if we want 40 meters in the east or positive x direction, we can write 40I. If we want 40 meters in the west or negative x direction, we can write negative 40I, and that includes the vector information is embedded in that I or j or k. And again, this might seem a little, why are we doing this? But you're going to see as we get to some practice problems what the real practical benefit of this is going to be. So up would be north, that would be positive j, down would be south, negative j. Out of the screen, out of the board toward us is positive k, positive z. Into the board is negative k. So here we've got a practice problem. We're going to talk about it in IJ notation and then also in R theta notation. A woman walks 30 meters west and then 40 meters north. Write her displacement in IJ and R theta. So the IJ is going to be super easy because they already gave it to us in IJ. She went west 30 meters, north 40 meters. So for IJ, we just have to write that down. Her x component of the hypotenuse is in the I, her y component of the hypotenuse is in the j. So it's negative 30I plus 40j. And that's how we would write it. We would write that her displacement r is negative 30I plus 40j. And that's a really handy way to do it, as we're going to see in a moment, if we have multiple vectors that we want to put together. This is a really helpful way to have it written. The R theta is maybe more intuitive to say, well, how far is she really from where she started and in what direction? This might be more intuitive to say, well, she's 50 meters away at such and such angle, but this is more useful for us when we go to combine vectors. So we're going to use those, right? We have the 2 sides of the triangle. We need to find the hypotenuse and the angle. We take the inverse tangent again, and this time we're going to get an angle of 53.1 degrees for phi. And then if we want truly the theta, right, measured from the positive x, that's going to be 180 minus this piece will tell us the other piece. So that gives us a theta of 126.9. And then we do a squared plus b squared equals c squared, or in this case, x squared plus y squared equals r squared. Solving for r, we take the square root, and we get 50 meters. So r comma theta notation, or polar notation, is 50 meters comma 126.9 degrees. Just another example here, working from town B to town A. We go 46 kilometers west and 35 kilometers south. We can describe that as negative 40I minus 35J. And again, whether it's plus negative 35 or whether it's just minus 35, it means the same thing. We can do the square root, get the distance of 57.8 kilometers. Take the inverse tangent to find that angle. I know that doesn't look the same, but that's what that angle is supposed to be. Opposite over adjacent is tangent. We get 37.2 degrees south of west. So they decided to describe it in terms of directions this time. Now, could we have translated it into theta by adding 37.2 to 180? We could have. That would have given us 217.2 degrees, but they're just showing you different ways. And again, I wish everybody measured and marked angles in exactly the same way, but they simply don't. So I've got to show you the different ways for when you run into different problems. So there's your theta. Another example, this one, another forces one, not a donkey this time, but somebody being helped off of the ground. They're pulling upward at an angle. Again, this is something that happens in life all the time, right? We exert forces and our forces aren't always all horizontal or all vertical. They're partially horizontal and partially vertical. So we need to be able to examine those individual pieces. So the yellow arrow is 240 newtons. That's how hard he was pulling, but he's pulling at an angle of 28 degrees. So we want to know how much of his pull is in the X and how much is in the Y. So we use our SOHCAHTOA relationship. The hypotenuse times the cosine of the angle equals the X, the adjacent component, which in this case is the X. We say negative because he's pulling to the left. And he's clearly pulling up. So we use sine to find the Y component. So in IJ notation, we could write this as negative 212 newtons I hat, 113 newtons J hat. Well, I say hat. Sometimes there are a little what looks like a caret from the keyboard above the I and the J, and they're actually pronounced hat in that notation to indicate, again, that it is a vector. So here's another force example, only this time we're pushing instead of pulling. We're pushing on the lawnmower at an angle of 32 degrees. How hard do we actually push it into the ground, and how hard are we pushing it sideways in that way? Again, we form our triangle. We have the hypotenuse value, which was given. The angle was given. We want to find these green arrows, the X and the Y components. Again, this is why we're learning about vectors. We're going to be doing a lot of this sort of problem in subsequent chapters, and I need you to be able to solve them without me having to reteach SOHCAHTOA every time. So we got a 254 newtons to the left, and I've got 159 newtons downwards. These both end up being negative because we're in the third quadrant, right? And again, these negative signs, in physics, negative signs often end up indicating direction, okay? So don't get hung up on the negative signs. It's not that, you know, somehow this force is different than if she was pushing the lawnmower to the right. It's just indicating the direction that the force is being applied. So sometimes the negative signs are very important when we are adding multiple vectors that are not pointing in the same directions, because those negatives will cancel with positive I values, right? But if we're talking about a single vector, those negative signs are indicating the direction for us, and sometimes we take the negative signs away and we indicate the direction in some other way. For example, in this problem, I could say she's pushing with 250 newtons to the left and 159 newtons down. So I've just taken the negative signs away and I've described the direction using words instead, which is acceptable and more meaningful to us often as humans. All right, so now we're going to talk about adding vectors, right? We did that graphically earlier in this presentation. Now we're going to talk about adding vectors using these components, using this I, J hat notation. And I think you're going to see that this is really a good way to do it, and a lot easier than getting out a ruler and measuring everything to scale and having to have your protractor to mark out all your angles. So again, we draw the vectors in the same way, right? We draw our first one starting at the origin. We draw our second one where the first one ended so that the second tail is touching the first tip, and so on through 2 or 3 or 4 or 67 different vectors that we're adding. And then our resultant is from the origin where we started to the tip of the last vector. And if we've drawn it approximately to scale, then we can use a quick common sense check, or we can make a quick check and see what quadrant we end up in. And then when we get our final answer, we can check back and make sure we're in the right quadrant. And then we write the vectors in IJ notation, and then we can very easily add the IJ notations and then convert back into R theta at the end. So Much easier to understand if we have an example. So here we have an example of a boat. It's going to move 4 different times in 4 different directions. So we got 2 kilometers east, then 4 kilometers north, then 2 kilometers west, and finally 2 kilometers south. So what is this going to look like? So we start drawing them, right? Starting at the origin, we draw 2 kilometers east, okay? And then we draw our second vector, 4 kilometers north, where our first one ended. And then we draw our third vector, 3 kilometers west, where our second one ended. And finally, our fourth one, where our third one ended. So you see, it's follow the leader, essentially, right? Each vector is drawn, starting where the last one ended, and we went almost around in a circle. And then our resultant is going to be from where we started to where we end. So we draw that in pink here, okay? So we can see we're going to be in the second quadrant, and that's what we would expect, a negative x value and a positive y value. So that's just the sketch to give us an idea. Now we go to the actual mathematics. And we write out each vector in IJ notation. Now these vectors are really easy because they're all either horizontal or vertical lines. We're going to do another practice problem a little later where there's actually angles to them, which makes it a little more challenging. But notice here how they wrote it. They wrote it as A is plus I, plus 2I, and is really plus 0j. B is plus 0I and plus 4j. And this way, you're going to see it's really handy to write it this way because now we have a column of I values and a column of j values, and all we have to do there is add the columns. Now again, if each of these had 2 values, that wouldn't be a problem, right? We would still add each column to get our total I and our total j. So we end up with negative 1I and positive 4j. We went back 1 and up 2 to reach our final location. And that clicks with our picture, right? That's what we would expect to be getting. 1 kilometer west and 2 kilometers north of the origin. See, they took the negative sign away and they indicated that direction with a word instead. So that is acceptable. They took the positive sign away also and said north instead. Now we got to convert it to the length of the pink vector and the angle that that pink vector would be at. Again, we do a squared plus b squared and take the square root to get the length of c, or r in this case. So it's the square root of 5. So 1 squared is 1, 2 squared is 4. That's 2.24 kilometers. And then to get the angle, we do the inverse tangent, which comes out to be 63.4 degrees north of west, right? We're starting in the west direction and we're going toward the north. So the phi, it's shown down here, phi is right there, measured north of west, 63.4 degrees. All right, last example. And this one has a vector that actually is at an angle that we're trying to add, right? We're adding 3 vectors this time instead of 4, 2 of which are in cardinal directions, but 1 of which is at an angle. What is a plus b plus c for the vectors shown? So a is 5 meters at 90 degrees. So again, if all they do is give you an angle, that means you're measuring it from the positive x-axis. So 90 degrees from the positive x-axis is straight up. So 5 meters straight up, that's A. It's got 0 x component and it's got 5 meters in the y component. B is 12 meters at 0. So 0 degrees is pointing along the positive x-axis. So there we are. And finally, C is negative 35 degrees. So it's 35 degrees below the x-axis and it's 20 meters long. So we've got A, and then we drew B where A ended and C where B ended. And now we have our resultant. Excuse me, R is being measured from the beginning of A to the end of C. So B was plus 12 in the X component and 0 in the Y. And then finally C, we're going to have to solve, right? We're going to have to solve this triangle to find the X component and the Y component of C. And that's what we're learning this chapter, is how to decompose vectors, right triangles to find the sides of the triangle, and then how to reconstruct them. So it's going to be 20 cosine of 35. Here's your 35. The x is next to it, so the x is going to be cosine this time, and the sine is going to be the y. So now we get all those values, right? We wrote them as a of x and a of y, but that's equivalent to I and j. So we got 0 and 5, 12 and 0. They computed this. You can compute this on your calculator. 20 times the cosine of 35 comes out to be 16.4, and negative 20 times the sine of negative 35 comes out to be negative. Actually, that should not be a negative. The sine of negative 35 should give us the negative sign. Should only be one negative sign, minus 11.5. So now we're going to add our columns. We get 28.4 I hat and negative 6.47 j hat. So those are our final I and j values for the pink, well, what's going to be a pink triangle. So we square them and take the square root. See here, they redrew that triangle, right? You can see this is what's physically happening, but that's going to leave us with a smaller triangle here, which they then redrew with the values from the previous slide. And we get the length, 29.1 meter, and then we do the trigonometry inverse tangent of y over x, and we get this angle theta. Now, again, notice they plug these in as positives, right? A math teacher would tell you that triangles always have positive side lengths, and we can go round and round with them. It depends, in my mind, what the triangle is representing. But a distance triangle, yes, always has positive side lengths. And so they did the inverse tangent here using positive values, but then they understand where this angle is, and so they describe it appropriately, 12.8 degrees south of east. Again, the description, the label is extremely important for the answer to be meaningful and useful. So now we have r and theta, and we've finished the problem. A couple final statements about vectors before we finish, and then, like I said, I'm planning to put some extra, if we were doing this class in person, I would have finished this lecture, and then I would give you some practice worksheets to practice this skill in class. And I would walk around and help you with it, and at the end of our time together, I would then give you the answers so that you could check your work. Because this is online, things are a little different. I still plan to give you blank practice papers posted in the Blackboard folder, and then also the answers posted. Again, this is about a skill. If you don't practice a skill, you don't gain the skill. Some of you are coming from different places. Some of you already have this skill. Some of you, this skill is going to be very difficult. Do what you need to do to achieve the mastery you need to get the grade that you want in this class. That's all I'm going to say about that. So a couple final items here before we finish the lecture about vectors. First of all, the location of a vector is irrelevant, which sounds weird, right? Because the difference between a scalar and a vector is that a vector has direction, but the location of the vector is not important. So on this little screen, you see A and B, and then it says that A is equal to B. And that's because A and B are the same length, and they are pointing in the same direction, even though they are not right on top of one another. So I think of this in very practical terms, right? So one example of a vector would be if you're giving somebody directions. If I'm telling my friend how to get to another friend's house, I say, well, you got to walk 4 blocks east, and then 2 blocks north, and then another 2 blocks east, and then it's the third house on your left. So 4 blocks north is a vector, okay? And 4 blocks north is a vector whether you're in Chicago or New York or Los Angeles. All of those 4 blocks north means the same thing, even though you're in different locations. So the vector can get moved around the graph paper. The vector can get moved around the country. It's still a certain length, and it's still pointing in a certain direction. So it's still the same vector. And the other thing is, what do negative signs mean for vectors? Obviously, a negative sign is not going to change the length of a vector, but the negative sign will change the direction. So C is pointing down and to the right. D is the same length, but pointing up and to the left. So C is equal to negative D. So if you stick a negative sign on a vector, you just change its direction. And by the same token, you can scale a vector, right? That's what we were doing with the I hat and the J hat and the K hat. They were 1-unit vectors, and then we were multiplying by them by a number, which was effectively stretching them out by a certain amount. So 2C is a vector pointing in the same direction as C, but twice as long. 3C is pointing in the same direction as C, but is 3 times as long as the original C vector. So those are just some final things about vectors. Again, practice your problems, and I'll see you in chapter 4 when we will start doing real physics.